Okay, aloha. My kako. Today we have a presentation by Rob, who is presenting a space for time substitution along a model hydrological system. So Rob, you may start whenever you're ready.
All right. Figure out how to share the screen here. All right, are the slides showing pretty well?
Yes, they are.
Okay. Good. Hello, everyone. Thanks for coming today. Got a pretty complex sounding title, but hopefully I can break it down into a more understandable format. I think unlike a lot of the other presenters throughout the year, we don't have new and novel research, so I'm kind of diving into the past a little bit to talk about how the stream research was set up. To start a little bit about myself, I'm a hydrologist at the Institute of Pacific Islands Forestry, which is known as IPIF. I've been here for about 5 years. Previously worked with the Bureau of Land Management and the U.S. Geological Survey before coming to Hawaii. Here at IPIF, I work with the Hawaii Permanent Plot Network, known as HIPNet, that has some climate stations, and then also monitor some streams, stream gauges along the Hāmākua coast. And there's my email address if you'd want to reach out to me. I'd like to just take a moment to pitch the Hawaiʻi Experimental Tropical Forest, HETF. There's the link. I would recommend that you take a look at that website when you get a chance. It dives into the history of the HETF, the background, some of the research going on there, some pretty interesting things if you're interested. And with that, go into the background of the stream research that's been going on at IPIF for about the past 10 years or so. Sorry, I had a mouse glitch there, not sure what happened. So there's about 11 sites that are part of the Stream Research Network here at the Institute. They were installed between the end of 2011 and the beginning of 2012. The stations are listed kind of going from Hilo up and to the northwest along the North Hilo Hāmākua coast. At each of the locations, there's about a 2-inch diameter steel pipe installed in bedrock or a boulder in the stream. And inside of that pipe is a cigar-shaped logger that's standalone waterproof, recording pressure, which is basically the weight of the water above that sensor. And from that, we can calculate the amount of water coming through. And the loggers are set to record every 15 minutes. And on that interval, the logger has space for about 6 months of data. So we have about 6 months before we start losing data. This is an overview map of the stream locations. So down just northwest of Hilo is Pahoehoe, the first station in the network, and it's on a small tributary to the Pahoehoe stream. And then heading north up to Kawaliʻi Gulch, we have a gauge on Kawaliʻi stream. This chart was taken from a paper, Climate-Driven Changes to Rainfall and Streamflow Patterns in a Model Tropical Island Hydrological System from Strauch et al. In 2015. And this is a good overview of what the design was for this stream research network. So they chose locations going along the coastline, trying to keep things as similar as possible between sites. Obviously, they're not all exactly the same, but they were trying to keep similar slopes, similar elevations, similar watershed areas, and similar land use. So trying to keep things as forested as possible. So now let's get into the meat of the talk, the model hydrological system, and then the space for time substitution. So what is a model hydrological system and what makes this a model hydrological system? So the mean annual rainfall along about a 20-kilometer stretch of the North Hilo Hāmākua coastline has a range of about 3,500 to 7,000 millimeters per year, which is a pretty strong gradient for a relatively short distance. Along this stretch, there's very little variation in mean annual temperature. The riparian plant community is pretty similar. Land use, while different, is fairly similar. Soil type and geologic age are also very similar for similar elevations. And because of this, we can kind of isolate the impacts from the variable precipitation to the stream flow and to the stream ecology. This is a illustration of that rainfall gradient. As you can see, we're pretty wet here in Hilo, but as you go north on the North Hilo Hāmākua coastline, it starts to taper. So we start out in this dark blue max rainfall and kind of move into the teal and green as you go north. And I don't know how detailed it shows up on your screens, but this little gouge here in the map is the Kavali'i Gulch, where our northernmost site is located at the tail end of the rainfall gradient. And I should mention that this came from the Rainfall Atlas of Hawaii, which is currently being integrated into the Hawaii Climate Data Portal. So I think it's kind of in a gap position now where you can't access it, but it will be available again in the future. Talk a little bit about the space for time substitution. So for Hawaiian Streams, climate change is expected to really alter the rainfall patterns, and it's expected to decrease stream flow and increase flash flooding. The rainfall gradient along the Hāmākua coast is kind of a model to project how changes in rainfall will impact stream flow and how that will impact stream ecology. The organisms that live there, nutrient transport, and such. Using this space for time substitution, we represent moving north along the coastline as moving into the future, essentially. So we anticipate that the drier northern streams will kind of be a reference point for the streams closer to Hilo that are wetter at the moment, but maybe drier in the future. And the important part of this is because the underlying geology and characteristics of the watershed, such as land use, forest cover, slope, soil type, are as consistent as possible. So we're trying to isolate that effective rainfall and its impact on the stream. So now we'll take those concepts and bring it into the HETF connection, which is why I'm here speaking with you today. So of the 11 sites, Kaiwilahilahi Stream is the only site within the Hawaiian Experimental Tropical Forest. This gauge was installed in 2022, and it has intermittent stream flow. There are three basic categories of streams regarding flow. There's perennial flow, where the stream is flowing year-round, intermittent flow, where the stream is highly dependent on rainfall patterns, and ephemeral flow, where the stream is basically only flowing after a rainstorm. Put this slide together just to show what intermittent flow looks like. So in summertime, for example, where rain is more scarce, Hawaiʻi Stream can be completely dry. And in the winter, like the image on the right, where rainfall is a little bit more regular, stream flow is more persistent. So you have more regular flows, and this is the same location on Hawaiʻi Stream where our gauge is at. This is a hydrograph of Hawaiʻi Stream from 2014, which is one of the years where we have the most complete data set. A hydrograph is kind of like a fingerprint for a stream. Each stream has a unique hydrograph based on watershed characteristics, such as how large the watershed is, the slope of the watershed, the underlying geology, how porous rock structure is, and such. So as you can see, as this intermittent stream goes throughout the year, when there's not a lot of rainfall input, flows are pretty close to zero until it rains, and then there's a sharp increase in flow and sharp drop back to zero. However, when there's more persistent rain, you see more spikes, and it takes longer for it to drop back to zero flow, that dry stream bed condition. And we have the hydrograph for 2015, another year where we have pretty complete data set. And I included this just to show the difference. So there's a lot of variability year to year in flow based on rainfall patterns, which we all know are not very consistent. So again, starts out at zero, and then as we get rain, it comes up and then falls back to zero. And you can see that the peak flows for this year were not as high as they were for 2014. And then just for comparison, although Kapue Stream is not within HETF, it's one of the most southern sites and one of the watersheds that receives a lot more rainfall. So I included it as a comparison to Hawaiʻi Stream. This site was installed in 2011, and because of that higher mean annual rainfall, it is a perennial stream. So for the 2014 water year, you'll notice that it seems like it's down at zero, but this is actually just an artifact of the scale of the graph. The peak flows are significantly higher. For this particular water year, the peak flow at Kapue is almost 6 times higher than the peak flow at Kaiwilahilahi. So it seems like it's dropping to zero, but it's actually not. It's just because the peak is up here at over 6,000 cubic feet per second. And I forgot to mention the unit of measure, cubic feet per second. It's not exactly equivalent, but a good frame of reference is to think of a cubic foot as a basketball. So this would be kind of like 6,000 basketballs coming through every second. And again, switching to 2015, we can see that it was a different year and the peak flows weren't as high. We only got up to 2,500 cubic feet per second this year. With the change in scale, we can see that the flows aren't dropping to zero. It still looks like it. They get a lot lower during this time period, but they're not actually dropping to zero. And if we could zoom in further, we could see that this stream has water year round. So those graphs, because they're over the whole water year, which I forgot to mention, extends from October 1st through September 30th, partially due to record keeping issues. There's not a great rationale for it, why they don't use the calendar year, but it is the way it is. But because we were looking at the graphs of the full water year, it's kind of hard to pick out details. So I'm going to put together a comparison between the two sites on a monthly basis. So it can be a little bit easier to see the differences between the two sites. So here is a graph of the monthly average stream flow from those two water years, 2014 and 2015, on a monthly basis. The dark blue is the Kapue monthly flow from 2014. The lighter blue is from 2015. So you can see the differences between the 2 years, with the 2015 high flows being substantially higher. And I should say that these are the average monthly flows. So on average, September had higher flows. This isn't the total flows, just the average. So for 2015, September was the highest average flow for Kapue. And then Kaiwilahilahi stream, the dark gold is the 2014 water year, and the light gold is the 2015 water year. So you can see from the graph for both of the sites for 2014 and 2015, January and February were the lowest stream flow, which was probably directly correlated to the least amount of rainfall for those 2 years. And because on average, the Kapue watershed receives a lot more precipitation, in general, it has a higher monthly average stream flow than the Kaiwilahilahi stream. So for the current status of the stream research, at the moment, we're in a period of collaborating with other researchers to fill the data gaps from 2016 to present, so that we have a complete data set for each of those water years from when the stations were started in 2011 and 2012 up through the present day. And the goal of gap filling these gaps in the record is to generate a complete 20 plus year stream flow report. And with that complete data set, other researchers will be able to take this stream flow analysis and use it to investigate changes in the stream flow during this period of time, but then also use it to forecast impacts to climate change, impacts from climate change to the streams in the future. For example, previous research has looked at nutrient impacts to the oopu, the Hawaiian goby in the streams, also the native shrimp, the opai, and how they respond to nutrient transport and nutrient availability with varying stream flows as you move north along the stream rainfall gradient. And if anybody is interested in those, I can provide links to papers that you can look into it further. I'd like to throw out a few suggested links in case people are interested in looking into things further. The first link is for the Institute's website. So if you're interested in all of the research that's going on here at IPIF, you can browse that link. And then also, as I mentioned previously, the Hawaii Climate Data Portal. It's an effort through the University of Hawaii at Manoa to integrate all of the climate data that's available throughout the state into one central location. So you could investigate anywhere from pinpoint near real-time data at a specific location, or look at historical data from, I don't know the exact limit, but let's say 40, 50 years ago, before data was hosted on websites. So they're looking to aggregate all the climate data that's available throughout the state into one central clearinghouse. And with that, I always wind up speaking faster than I thought I was going to. I'd like to wrap up and thank everybody for coming and open it up to any questions that anyone might have.
Perfect. Thank you so much for coming and sharing your research and what's happening with the streams. And I look forward to kind of seeing the fruition of that main report of the past 20 years of how climate has kind of impacted the streams here and how it's going to continue to impact our streams. So does anyone have any questions? You guys feel free to unmute yourselves and turn on your video. Oh, we have a question. So Kealoha said, are there any diversions in the network? Well, I can't read the rest of it.
Sorry, I can fill it in and write that very good. Sorry, but hey, Rob, that was a great presentation, and I guess I just had a question about, like, I know historically there have been diversions across the that area for sugarcane and timber and so forth. And I just wondered, are any of those diversions still active, or are they all have they all returned to the natural flow of the stream?
Very good question. I am not aware of any active diversions on the streams that we are gauging, which doesn't mean that there aren't any, but I'm not aware of any. I am aware of, I guess, 3 historic diversions on the streams that we're looking at, and there may be more that I'm not aware of. At Manawaiʻi Stream, which is near the Kahikina Learning Center, I believe it was for agriculture, but I'm not certain. There is a dam across the stream that's no longer fully functional. Basically, it's leaking. It's just a very small dam, but I think it was for irrigation purposes for agriculture. At Kolekole Stream, there was a low-level dam that appears to have stretched across the stream at one point. It's kind of only available on either, or not available, but still intact on either edge of the stream. The middle is kind of blown out. That appears to have been a larger scale diversion for sugarcane.
Yeah.
And then also at Uma Stream, there was a similar diversion that appears to have been for sugarcane, but is no longer active.
I have a follow-up question. I don't know if anybody's waiting, but well, actually two follow-up questions. So one, are any of those diversions impediments to Oʻopu migration, or are they all are they able to navigate those?
So at Kolekole Stream and Uma Stream, they are not anymore because the dam structure is not intact across the stream anymore. At Manawaiʻi Stream, I believe that it would be an impediment because except in the most high flows, which I've actually not seen in person, I don't think that flow actually passes over the dam to create like that cascading waterfall effect that they would be able to climb. So the dam structure itself is dry from normal flows. So I don't think that they would be able to scale that and get above it. So the flow leaks through the dam, which I guess maybe if the corridor that it's leaking through was big enough for the fish to travel through, it might be able to, but my gut, I guess, says that it is an impediment to Oʻopu traveling upstream beyond that point.
And then I guess, and then my very last question, I promise. And this is sort of like going to sort of like what we expect to happen because of climate change, and that it may impact the availability of water across streams that are in certain areas, right? Because you kind of have I think there's like a gradient, right? As you move across, and that's what makes it such a great place to study. And I guess one of the question I was thinking about as you were talking was in the same thread as the diversions were used for moving water for sugarcane and timber and other things. Do you think it's possible to manipulate the headwaters of certain streams to feed into other streams? In the event that like, you may lose some streams that are in the drier areas, but I wondered, could they, instead of like taking the water out for industry, could water also be diverted into streams to preserve the function of that area? Or yeah, I don't know. Anyways, it was just hopefully I worded that well enough, but it was just an idea.
I think I understand what you're asking.
Yeah.
And short answer is yes. Yes, it could be possible. But it's a very complex thing. And so there are a lot of challenges because the volcanic flows are very drawn a blank as to the word, but basically not homogeneous. So you have all of these different fractures and conduits and even lava tubes. It can be really hard to put water in one place and expect it to stay there. It kind of goes where it wants to. And then the other aspect of that is it often comes down to funding.
Yeah.
Because water wants to travel downhill the quickest way possible. So we have to get it up and over ridgeline into another watershed. It requires a lot of energy input, which usually is pumping, which is costly, and that sort of thing.
Yeah, it's probably just super complex. I guess I wonder that for, a few reasons, for the Opu, for these, for all the other stream people. But then spending time in Waipio, spending time with kalo farmers that rely on the stream water, like it's a real concern, like what's going to happen in the future, like is that resource a threat? And then and if so, like what can be done to make sure we don't lose that completely,
You get it by 2 o'clock? 2 o'clock?
By 2 o'clock? Yeah, 2:30.
Get it to me by 2 o'clock.
Oh, wait, you at 2 o'clock.
Okay, because then I can get it, and I can put it all together.
Yeah.
You guys can do it.
Yeah, we do.
You're doing it.
Yeah, I guess as an example, it's definitely possible. You can look at what happens at the Hoover Dam, where water is taken from the Colorado River, pumped up through the mountains and down to Los Angeles. So it's definitely possible. It's a matter of resource input.
Yeah, hopefully we never get to that, and we can avoid that in other ways, but
right.
I worry about our kalo farmers sometimes, like all these different changes.
Yeah.
Thanks so much, Rob. We appreciate all the work you're doing, and thanks for a great presentation.
Thanks.
Yes, thank you for that wonderful presentation. Does anyone else have any questions? I mean, if not, I think you'll all know where to find Rob, or you can reach out to us, and we can connect you. Grace said thank you. I believe Sarah also put mahalo Rob in the chat as well. If that anything, we can close up the webinar early. Keloha said mahalo. We do have another webinar in August. Becky Ostertag is presenting what are lessons learned from the long-term forest monitoring data of the Hawaii Permanent Plot Network. So be on the lookout for that, and you can register for that Zoom. hopefully probably by the end of the week. But if anything, I want to mahalo you all for coming to the webinar. Yeah, thank you.
Thanks, everyone. And for the benefit of the recording, feel free to reach out with any questions. Thanks a lot.